Hi there. In this video, I want to talk about overcoming exploration in reinforcement learning with demonstration. This paper is published in 2018, and it's being used in many applications, especially when we have some demonstration to be used when we are training an agent. That demonstration can be uh, another agent that can do some task elegantly and very precisely. So those information from another agent can be used for training a different agent. And another thing is that sometimes in some tasks we know that when we are in one state, what is the best action to take. So we can create a data set as a demonstration. Let's see some of the sentences in the paper. At the end, I will implement a torch version of the paper. Exploration in environment with a sparse reward has been a persistent problem in reinforcement learning. And they said our method, which builds on top of deep deterministic policy gradients and hindsight experience replay, provide an order of magnitude of speed up over reinforcement learning on simulated robotic tasks. I highlighted this sentence because this was important. First, it is based on deep deterministic policy gradients. It can be used for off-policy learning. Also, they mentioned about the hindsight experience replay. So we have a replay buffer, and we put that demonstration in that replay buffer, but there are some terms. They do not take the demonstration if they feel that the action selected by the optimization policy is better than the action by demonstration. So this is another rule that they are applying that. So they mention here, many robotic tasks also require executing multiple steps successfully over a long horizon, involve high dimensional control, and require generalization to varying task instances. They also mentioned about the behavior cloning here. So the way that they are applying the demonstration is behavior cloning, and they are talking about Dagger. Dagger is a method that it's one of the methods for behavior cloning, but they mentioned that it is difficult to use Dagger in practice because we need an expert. In Dagger, we try to train an agent using an expert, or sometimes even using some classifier that know which action we should take. But in demonstration, we demonstrate some of the tasks. We don't need to have an expert or a complete system or an agent trained. Maybe we know some of the demonstration, we can just highlight those for the model. We're working on the deep deterministic policy gradient, and we want to train a model that by giving a state and action, we want to predict the reward. So if we can do it, we can simulate an environment, because we know that in that environment, if we take what action, if we are in one state and we take an action, what reward we can get. So the Q action value function is like mimicking an environment. In DDPG, the deep deterministic policy gradient, the algorithm work based on increasing the rewards over the time. The gamma here is a discount factor for future rewards. So the paper mentioned here that we want to optimize this. They mentioned about the Q value. So you know that we have like critique model. So what is the difference between critique model and the Q function? They're mentioning to stabilize learning, the Q value in equation 3 is usually computed using a separate network called the target network, whose weights are an exponential average over time of the critique network. So basically they are same. So the critique network and Q state value function are same, but the Q function is the stabilized version of the critique. In each iteration, we are training the critique, but after one complete epoch, we update the Q value function. That's why the result is a smoother in target values respecting to the critique values. So, so far we have defined these laws. This is the loss DDPG, as mentioned here. They are combining these laws and the behavior cloning loss. So for behavior cloning, we are saying that if we have some demonstration, we want to train a policy network that reduce the loss, reduce the action prediction between the demonstration and between the policy network. It means that we want to train a policy network that follow the demonstration. But there is a point here that we want to reduce this one and increase this one, because we want to increase the rewards and reduce the difference between the action defined in the demonstration and the policy network. That's why we have a weight of the first loss. We want to maximize it, and the second one we want to minimize it. That's why we have a negative value here. And another important factor here is they are not always getting information from demonstration, but sometimes the action we predicted by the model is better than the action that we have in demonstration. So this gives the model opportunity to even getting better than the demonstration. In this case, they are saying we are not taking the behavior chronology loss. We are just taking that when reward we get from the demonstration is bigger than the reward that we get from the policy network. So this is another important factor. And they said here, we account for the possibility that demonstration can be suboptimal by applying the behavior chronology loss only to a state where the critic Q determines that the demonstration action is better than the actor action. So demonstration can help the system to find the optimum goal faster and better convergence rate. So this is an overview of the paper. Finally, they have some experiment compared with others and showing that they can get the rewards very faster than others. And yeah, that's it. This is very simple, but very effective. So finally, it is important to know that the learning from demonstration is off policy, because we always do continuous exploration. So the agent can learn policy, and it can also select between the demonstration and their in its own exploration. That's why they use a DDPG, because it is off policy. So if you're using an actor critic model, so the critic model can be used for updating the queue, an actor model can be used for the policy. So this is not really the policy, this is the actor model that we set the state and it can give us the action. Yeah, that's it. So let's start to code for learning from demonstration. As I said, I'm using a code from policy gradient is all you need repository. So this is not mine, but we're trying to explain each line. We have a replay buffer, and for replay buffer, it's just a simple class, and we get the observation dimension, the size that the replay buffer has, and the batch size that we have. And we have a store function. So anytime that we say we want to store things, we can store the observation, the action, the reward, the next observation, and is it done or not? Very similar to what we did for the previous project. And also we have the extent. So we store new transition, and also we sample batch. So we randomly sample a batch of experience from the memory. Also demonstration will be added to this replay buffer as some experiences that we had from before. We want to define the actor and critic network. So the actor network is just some linear layer, and we initialize them by the uniform distribution. That's very simple. And we just apply the ReLU activation, one linear, and finally we get the action. So the actor function is pi in the formulation. So we get the state and we want to predict what is the best action. So for critic network, we are getting the state and the action, and we are saying what is the reward of that. So if we are in one state and we do that a specific action, what reward or what value we will get from it. So this is very simple to the previous network, some linear layer and the value, which is the reward. So this is as the Q, the state value function that we have. So the critic is the Q function, but as we explained in the paper explanation, it is not exactly the same. It is just exponentially average of the critic. The Q is the exponentially average of the critic, and the actor is the pi. So these are two networks that we define. So now it's time to create a behavioral cloning agent. So first we need to gem for creating an environment. And we have a memory size, the replay buffer size can be defined here. Also, the batch size can be defined here. And we have a demo batch size. I will talk about them. We can have noise for exploration because, as I said, this is an off-policy algorithm, and we are more prone to explore the environment. And there are some methods to apply the noise to the exploration. So we not get the action exactly, we add some noises to it. These are the lambda, the loss parameters that we had in the paper. The first one is related to the DDPG, and the next one is related to the behavior cloning. So for initialization, we get the shape of observation and get the shape of action. And all of the variable we defined up there, we just initialize them. We haven't defined the OU noise yet. For simplicity, I can't remove it, but let's keep it to be same as the source code. And finally, we select that this is based on the GPU device or CPU, and we define an actor and critic methods. And as we said, we have a target, and the state is same. The state of the target is same as the state of the actor. And also for critic, we are creating a critic target as the Q function. So just to have exponentially average of the critic after some epochs, we set it as a Q network. And we define two optimizer for actor and critic. And yeah, that's it. We need some function here. First is select an action. So we need select an action from input state. So if we are in one state, what action we can get? So how we can do it? While we are in the training, we want to do exploration. That's why we apply we get some sample from the environment, and we selected the action. And after that, we add some noise to it. But if we are on a test, so we want to just get the action from the actor because actor is trained. That's why we get the action from the actor by passing the state to the actor and detach it and put it in the CPU and NumPy if it was on the GPU. And we select that action, but this time we do not add any noise because this is on test and we are not exploring. So we return the current state and selected action. This is the first function. We need to write the step function. So we can say BC agent go one step, which means that we pass an action and we say go one step and we get the next state and reward. And if we are not in the test, so it means that we are in the training, we need to save it in the memory. So we say memory store that transition. If you remember the replay buffer that we have here, we have a store function. So we can store that transition. So we say that if we go one step, save that step in the replay buffer. So now it's time, after going some step, we need to update the model. Suppose that we have created some trajectory, we need to update the model. And for that, we get a batch from the replay buffer, we sample from it and just convert it to torch examples. I mean, tensor examples, and we have sampled the state, the next state, and what action should we take to go to that next state, the reward, and is it done or not? And also we sample from the demo buffer. The demo is a demonstration buffer. So we will create two replay buffer. One is the memory, which is the replay buffer for our actor critic model. Another is the demonstration. So we get one sample from the replay buffer, one sample from the demonstration buffer. Yeah, so if you remember the first formulation of the paper, it was, you remember we had a y and we had reward plus a gamma, and after that we had the q value. So we can have it such that we have a next value, which is a q value, and if it is not done, we can multiply it by the gamma and plus the reward. So we have the current return. We can define what is the current reward that we could get. And for training the critic network, we can train it using this current return that we got. After that, we have the PG loss. You remember DDPG, this is the DDPG loss. And yeah, if we go back to the paper and see the PG loss, the PG loss is defined we apply the state to the actor and to the critic network, and we calculate their average. And the negative value here is just when we want to sum it up with the BC loss, we can do it easily. So, and the next step is to calculating the BC loss. So for BC loss, we use torch greater. We detect if this one is greater, we pick that one, otherwise we picked another one. This is the mask that we had, the condition that we have, that if the action selected from the demonstration is better, we use that. And finally, the loss that we have is the lambda 1 in PG loss plus lambda 2 in BC loss. So if the demonstration wasn't good, so we are not applying the behavior cloning loss. So that's why we set it to the 0. So, and finally, we optimize the actor model. And we have soft update here that I will talk about it now. The soft update is the exponentially average of the actors and critic. We need to define a tau because the exponential average is defined like this. And each time we get the parameters of the actor that can be applied for the critic too, but let's see this part. So we get the parameter of the actor, and for each parameters inside, we use this formulation to update the parameter of the actor target. So all of the parameters from the actor is moved to the actor target by this rate. And this is applied for also for the critic. So for training, first we said that this is not a test, and we reset the environment, and based on the number of frame that we want, we get an action, select an action using the resetted state, and we step forward, and each time we get a reward, we add the reward together. And if episode is done, we reset it and we save the scores. If training is ready, so it means that the memory is full and maybe the total step is bigger than the initial random step. So we pass the number of required steps. So we update two models and we just append the losses just for plotting. And after some step, we just do the plot. So I will show the plots. So we get the frame index, the scores, the actor loss, and critic loss, and just show their losses. And another function we need to define is the test. So we want to test the agent. Maybe I can define it before the plot because that's more relevant. For testing the agent, we set self is to false. And again, we reset the environment and we render the environment and we get a frame and we select action and we step forward that action until it's done. So we save all things in the frames and we return the frames. So another thing that we need to implement is when we are adding the noise, we are clipping them to be between -1 and 1, but sometimes it's not plausible. So there are some classes in the gym that we can normalize the action. So I can define it in top of here. So I can say action normalizer, that we need to get an action and get the lower and higher dimension of it and normalize it using some factors. And we need to reverse it when we want to apply it to the environment. So what we want to do with that is we want to create a gym environment, and this is Pendulum V0, and we want to action normalizer. We apply that to the environment. So for demonstration, we are using a pickle file. So demonstration is a pickle file, which is another agent model that is well trained on this task. Finally, we need to define number of frames that we want to train on, the memory size, the batch size, the demo demonstration batch size, and the noise parameters and initial random steps, and we can train our agent. For training our agent, we just need to say agent.train based on the number of frames. So another thing that remained is the noise function. I will not go through the noise
function specification, but we get one state and we just added dx based on um, parameters mu. It means that like a little change from the current state is applied to the system. Yeah, so we need to import some of the libraries. So I like to run these and see if it is works or anything is wrong. So I got the demonstration from another agent which is trained by DDPG, but with no demonstration. So currently we have the replay buffer, the last replay buffer of that agent here. So we use this demonstration, and I also change a little part of the code because I have the replay buffer. I don't need to like extend it, create another class of replay buffer. This is currently a demonstration replay buffer. So if you have some demonstration in the format of the replay buffer, we have to add it to the class, but currently this is a sample of that class. So we just assign it to the demo memory, and yeah, everything should be fine. I run it, yeah. Let's see how it is performed after some epoch. So you see that after small epoch, you see the loss is changing and the critic loss is changing. If you run only the DDPG, it doesn't have any demonstration, and the convergence on this technique is really better because we are using the demonstration. So the agent can learn the better way to complete the task. So we wait until this is finished, and finally we can get the images, and I show you the images. I will pause the video and back. So the model is trained for 50,000 frames. And also I added this part that it can show us how is the animation of the pendulum if we see that. So it's showing us for some frames. Can also I'm saving a GIF file beside it. So that's it. This is the demonstration. This is very similar to the DDPG. The only difference is that we have that demonstration, and we apply that loss, that sometimes we pick the action from the demonstration, not from the policy or actor network. So that's it. I hope you enjoyed the video. Please leave comments, subscribe, and share with your friends. Thank you and have fun.